Alrighty, ladies and gentlemen, welcome to the practice test video for our redox test. So let's take a look at what we've got here. Alright, the oxidation number of iodine in KiO4. Alright, so our known oxidation states would be the K and the O. So we know the K and we know the O. Potassium is a group 1 ion, so it's a +1, and O is always -2. Okay, always, always, always. So what we're going to do is set up our algebraic way to do this. So I'm going to say, okay, I got 1 plus 1, so 1 potassium, plus my iodine that I don't know, plus my 4 oxygen, so 4 minus 2's, and I know the whole thing is equal to 0. Alright, so if I take a look at what this is, I've got 1 plus my iodine plus 8, so that's 9 on that side. Oh, plus -8, I'm sorry, plus -8. And so that's going to be a -7 plus my iodine is equal to 0. So that if I add my 7 over, I do get +7 as my answer. Alright, let's take a look at the next one. What is the oxidation number of sulfur, N2S2O3? So I'm going to give us some more room to do this one. So I'm looking for the sulfur this time. That means that I know the sodium and I know the oxygen, so same deal here. I'm going to take my 2 sodiums, add a +1 because they're a group 1 ion, plus my 2 sulfurs that I don't know, plus my 3 oxygens that are both a -2. The whole thing is equal to 0 because the compound is neutral. So I have 2 plus 2 sulfurs plus -6 is equal to 0. So if we simplify, we've got -4 plus 2s is equal to 0. Add my 4 over, and I'll get 2s is equal to 4. Divide by 2, and s is equal to +2. This is exactly what we see. Do you need to show all of this work? If you need it to get to the answer, yes. If you don't need it to get to the answer, no. Alright, so just do what you need to do. I showed the most work possible, but I recommend doing as many algebraic steps as you need to do. Alright, number 3. Given the balanced equation representing this reaction, the oxidation state of chlorine changes from a what to a what? I think we've actually had a similar question to this. We've got chlorine over here, and we've got chlorine over there. The easy way to do this is to know, okay, K and Cl, so this is a +1, so this must be a -1, so I know that I'm going to end up a -1, so that leaves me with D, and it leaves me with C, so A and B are out. So now I need to figure out what's chlorine over there. So what I do is I go, okay, potassium, there's 1 of them, +1, plus my Cl, plus my 3 -2's, all equal to 0 for my oxygens and for my neutral compound. So I have -6, which is right here, +1, so that's a -5, plus my chlorine is still equal to 0. I'm going to add 5, and I can see that my chlorine starts at a +5 on that side, which is good. Alright, for number 4, we get a nice easy one. Oxidation reduction reaction, the number of electrons lost must be equal to the number of electrons gained. That's the whole point of this, that you can't gain more than you lose and lose more than you gain. Everything's got to equal out. That's that concept of conservation of mass, which is, or mass and charge in particular, which is so very, very important to us. All right, for the next one, we have number 5. Given the balanced ionic equation compared to the total charge of the reactants, the total charge of the products is what? Okay, so that again goes back to the same concept of conservation of charge. So if I have a +2 charge over here net, then I should have, I don't have a +2 charge. I have a 3 times 2 plus. I have a +6 charge over here. Then I see over here I have 2 times 3. That's also a +6 charge on this side. and these guys are 0, so they don't contribute to the total charge. I have the same charge on each side. That's why this is a balanced ionic equation. So that's why the same is the correct answer. All right, which metal is more active than H2? This is a lovely way of asking you to use Table J. Hopefully you all already knew that. So more active means higher than, and then it's implying that we're using Table J, so higher than H2 on Table J. The only one that fits that bill is lead. All right. 7. Here's the balanced ionic equation representing this reaction. Which reaction represents the reduction that occurs? Well, here's a nice opportunity to remember what reduction means. It means red cat, sure, but we're not there yet. It means grrr, as in gain electrons. Reduction. So that means they are added as reactants. So we can only pick something that's added as reactants, and we also know that the oxidation number literally goes down, okay? It literally decreases or is reduced, okay? So we're going to see here, well, which one literally goes down? We have a 2 plus to a 0, so it looks like copper is going to be the one that's at, so get rid of A and B. And then we know that we're going to gain electrons, so which is the one that gains? We got D as our answer. 8. Which half reaction correctly represents reduction? Once again, we're doing the same thing. Okay, we've got to have our oxidation number, first and foremost, needs to go down, and then we also need to add electrons as reactants. Okay, so if that's the case, we see that A is wrong, the electrons are a product, and our number goes up. B, our number goes down, but the electrons are in the wrong spot. D, our oxidation number goes up, which is wrong. Okay, so C is the correct answer. 9. Which reaction is an example of oxidation and reduction? All right, so here's what you are looking for. So you need some element that is alone, then in a compound, or vice versa. So it goes either way. I don't really care whether it's in the compound first or then it's alone, but take a look at what our correct answer is. We have K in a compound as a +1, and then K alone, it's a 0. It's an implied oxidation number change. You don't have to know it goes from a +1 to a 0, but you have to know that it goes from something that's non-zero in a compound, because it can't be 0 in a compound, to something that is 0 when it's alone, okay? If you take a look at all the other ones, you're also going to see that, hey, look, they are double replacements. And we know that double replacements are never redox, okay? All right, 10. Which metal reacts spontaneously with a solution containing zinc ions? So this question, zinc ions, means I've got Zn2+. That also means that I have zinc in a bond, basically. That's the way zinc would be in a bond. So that means that something needs to, quote, replace zinc. So I'm looking for something more active than Zn in order to essentially reduce it. Okay, and the only thing more active than zinc is magnesium. Next, I have 11. Which term identifies the half reaction that occurs at the anode? You should all know this. Anode of an operational electrochemical cell. So we want to remember an, active, ox. And that ox tells us our answer. It is oxidation. All right, so for number 12, what is the coefficient of the SO2 when this is correctly balanced? This is a bit of a toughie. So what we are going to do is figure out our oxidation numbers first. All right? So I'm going to move over to the side to do this. So I've got IO3 minus, and I know that oxygen is always going to be a -2, so 3 -2's. And my iodine, which I don't know, is equal to -1. It's equal to -1 because I have that negative ion there. okay? So I have ion plus -6 is equal to -1. I add my 6 over, and I get that my iodine is equal to 5. So I'm dealing with a +5 over here, okay? Now we're going to take a look at the other. We have SO2. Well, I can do this one with kind of out doing the algebra. I've got oxygen, there's 2 of them, at a -2. So that means this S must be a +4 to balance that one out. Then I take a look on this side. I see my iodine's alone now at 0. So I know it goes from a +5 to a 0. And my sulfur, this one I am going to move over and kind of balance out over here because we've got a different charge on it. We've got sulfur plus 4 oxygens at -2 is equal to -2. So we have S plus -8 is equal to -2, and my 8, S is equal to 6. So now I'm going from a +4 to a 6. So what I'm going to do is write my half reactions. I need to figure out which one's oxidized and which one's reduced. So the easiest way to figure out is which one literally went down. So I can see that the iodine went down. It went from a +5 to a 0. So the reduction is going to be the iodine, and that means the oxidation is the sulfur. Oops. So let's see what we can do here. All right, so I have iodine plus 5. I know that's going over the side, but I have it here. Iodine plus 5 yielding I2 as a 0. Okay, so this is the reduction. I'm going to add 5E minus. But here's the tricky part. I know that there are 2 iodines there and only 1 iodine here, so I'm going to put a 2 in there in front of that guy. So now there's 2 iodine plus 5s, so that means I should have 10 electrons. A little tricky. Now I go back to my sulfur. I know that the sulfur started out as a +4, and it goes to a +6. So it goes to an S plus 4, yielding S plus 6 plus 2E minus. So now we've got a balance here. And the easiest way to do this is to multiply through by a 5. So that way I still get 10 electrons, which works. And so now I take a look back, and at my question it says, what's the coefficient of the S2? Well, I can see what the coefficient is going to be. When I distribute this 5 to everything in the S half reaction, it's going to go to everything with an S, which happens to be this guy. Plop a 5 over there, and that's going to be my answer. All right, let's take a look at 13. All right, when this equation is balanced, both Fe3 plus and Fe have a coefficient of what? So what we have to do here is balance this guy. We've got to make sure that we have our charges set. So there's a couple of different ways you can do this, but because I want practice for you guys writing the half reactions, I think that's the easiest way to do this. I determine that magnesium is oxidized, its charge goes up. That means that my Fe is reduced, its charge goes down. So it starts as an Fe3 plus 3E minus yields Fe solid. Okay, that's my reduction. Then I see Mg0 yields Mg2 plus 2E minus. So you can kind of see what happened here. Magnesium got multiplied through by 3 to get 6 electrons. So that means my Fe got multiplied through by 2 to get 6 electrons. So that means 2's plopped in there. And so we take a look at what our answer is. 2, which is what we got, because the total of 6 electrons are transferred, which is exactly what you'd get here in our half reactions. So it is nice and easy to see when you do that out. 14. What half reaction shows conservation of charge? Meaning same on both sides. All right, so we take a look. A, -1 plus 1, not the same. C, +1 minus 1, not the same. +2 minus 2, not the same. +2 minus 2 on the same side, so 0 and 0. Hey, that is the same. All right, 15. Which Redox reaction is correctly balanced? So again, charges are the same, and then most importantly, again, too, that our masses are the same. And by masses, I mean the number of atoms of each type of element. So if we take a look, let's look at D, for example. I've got Zn and Zn, so 1 to 1, and 2 Brs and only 1 Br. Nope, mass is not balanced. 1 Pb, 1 Pb, 1 Ag, 1 Ag. Ooh, this is looking promising, but look at our charge. +1 and +2. Not balanced. Let's take a look at A. 0 and 2 already. I can see that's not balanced, so B it is. All right. Let's take a look at 16. This is correctly balanced using the smallest number of coefficients. The coefficients of Pb2+ will be what? So let's take a look into our half reactions. This time, I'm just going to have the half reactions come up to the side in a second. So you can see the half reactions that I wrote out here. We've got 3 electrons here and 2 electrons there. That means I need to do my nice multiplication through. So I'm going to multiply this side by 3 and these guys by 2. And so a correctly balanced equation, the coefficients of the PB will be, well, what did we multiply through the PBB? By 3, and 3 happens to be our answer. All right, oops. All right, 17. During the operation of a voltaic cell, the cell produces electrical energy spontaneously. That's just something you kind of got to understand. That's what a battery is. If it didn't produce electricity, it wouldn't power your cell phone, and it wouldn't be useful to us. So that's why we like them. All right, 18. Which process occurs in a voltaic cell? Again, same question basically. Chemical energy converted to electrical energy. Your cell phone runs on a battery that is voltaic. It takes an it takes a chemical reaction and it produces electrical current. That's why my laptop runs. That's why this iPad works. This is why everything that runs on a battery works, because it produces that electrical energy that we need as the end result, as the point of the process. And again, remember that that is different from an electrolytic cell, which is the last cell that we talked about, which takes a battery and uses that to power a non-spontaneous reaction. But different thing. That is not voltaic. Voltaic has electrical energy as the product. All right, 19. Base your answer to the following questions on this diagram. When the switch is closed, which half cell does oxidation occur? All right. Oxidation, I remember, an active ox, and so I remember that of my metals, Pb and Ag, whichever one is more active, that'll be the anode. So in this case, looks like Pb is more active than silver. So that means this guy is going to be the anode, and the half cell will occur in half cell number 1. All right, 20. Which is true for an electrochemical cell? The oxidation occurs in the anode only. Well, see above, because that is correct. An active ox, it only happens in the anode. 21. Which component of the electrochemical cell is correctly paired with its function? All right. I've talked nothing about conductors. But we have talked about salt bridges. You'll get 75 million more questions that are about salt bridges. This is a very common thing to ask. Salt bridges permit the migration of ions, and they also keep the cell neutral. There is no fancy thing I can tell you other than to remember that, and to remember that the salt bridge is one of the thing that makes our battery work. If you don't have the salt bridge, you don't have anything. So please make sure that you know about the salt bridge. 22. Diagram below represents the voltaic cell. Which statement identifies the part of the cell that conducts electrons, and describe the direction of the flow? Well, guess what? We know that electrons flow through the wires, and unless you want me to play a certain song for you again, hopefully you remember that electrons flow from anode to cathode, and in this case you have to determine which one's the anode. So the more active metal would be zinc, which is my anode. The less active metal is nickel, so it flows from zinc to nickel, anode to cathode. We've got D as our correct answer. Next page, 23. Base your answer on the following questions and information below, blah, blah, blah. Explain in terms of zinc atoms and zinc ions why the mass of the zinc electrode decreases as the cell operates. Well, this is an interesting question because we know one thing. We know, well, first off, that zinc is the anode. It's more active. We know that iron is the cathode. And I made a point to point out to you that the cathode does something peculiar. It gains mass. And we know this because the half reaction that occurs at that Fe, where we have Fe3 plus 3E minus, yielding Fe solid, we know that this side gains mass. But now it also makes sense then that this side would lose mass. And if that's the case, think about the other half reaction that's going on here. We have a Zn, and we have that solid electrode, and the oxidation that occurs means that I take the solid zinc that I have, and I don't produce more solid zinc. I actually produce zinc 2 plus ions plus electrons that then flow through the wire. I'm losing this electrode. Okay, I'm losing mass here because it's being oxidized away. It's being oxidized and plooping down into the solution of zinc ions and then electrons. So this electrode is slowly fiddling away. So any explanation that hints at any of the topics that I just discussed, saying perhaps the oxidation that is occurring at the anode produces zinc ions from the electrode, decreasing the mass of the electrode, that would be an appropriate answer. 24. What is the correct reduction half reaction that is occurring? I'm actually going to have you cross off this question. No worries. I bet you guys can do it anyway. All right, next one, 25. This is a very similar question to the previous one that asked about the electrode decrease, and the answer is very similar. The reason it's on here as well is because this is no longer a voltaic cell. This is an electrolytic cell. And so that makes it operate just a little bit differently. So in terms of Ag and Ag plus ions, meaning I have to specifically talk about them, why does the mass of the silver electrode decrease? Well, this silver electrode is acting as the anode. So you could say at the anode, Ag solid is being oxidized to Ag plus ions. All right, 26. Base your answer to the following question on the information below. Got another voltaic cell. What is the purpose of the salt bridge? Well, this is a nice question. Looks like we don't even need the diagram. You can say two things. You can say allows ions to flow. Then you can say keeps cell neutral. And both of those will be perfect. Alrighty, only a couple more questions, even though it's 2 more pages. Write a balanced half reaction for the reduction that occurs in this cell. Alright, so what we need to figure out here is which one is the anode, which one is the cathode. So Ag and nickel. So nickel is clearly going to be more active. This is my anode. This is my cathode. And then I know an active ox, red cat. So that means my nickel is oxidized. Okay, and that means my Ag is reduced. So my question is specifically asking me just for the reduction. So I'm going to do my reduction of the Ag plus to the Ag solid. Take my Ag plus 1E minus, yielding Ag solid. That's it. all you need to do. Okay? Pretty good. Pretty good. And that's the answer key. Look at that. All done. Alright, if you want that, it's on the screen here for a minute. You can pause if you wanted to see any of it. There you go.